the visitor from beyond, an extended journey. They found it in the dark between stars, a visitor that moves wrong. From beyond the solar edge, something crosses toward us, not wandering, but arriving. Telescopes caught its shimmer first, faint, deliberate, impossibly distant. Light bends around it like memory bending around truth. The instruments hum quietly. The data whispers the same message again and again. It came from outside. Through the void between suns, it drifted for millennia, carrying cold older than our planets, silence older than our words. Now it passes through the solar system, slow, patient, as if remembering a path once traveled. Scientists call it Three-Eye Atlas. The ancients would have called it by another name. In clay tablets buried beneath sand, the Sumerians spoke of sky travelers who return when the heavens align. Beings they called the Annunaki, those who came from heaven to earth. And now something glows against the darkness again, following coordinates written before writing existed. It's moving closer, and the night sky remembers. The discovery didn't announce itself with fanfare. No press conference, no immediate headlines. Just data accumulating in servers, algorithms noting discrepancies, automated systems flagging coordinates that required human attention. In an observatory perched on volcanic rock, miles above sea level, where the air thins to almost nothing, an astronomer noticed the alert. Another point of light that didn't match the stellar background. Another moving object crossing the field of view. At first, routine. Space is full of motion. Asteroids drift through the inner system by the thousands. Comets swing past the sun in elongated orbits. Satellites trace artificial paths overhead. Most moving objects in astronomical images have simple explanations. But this one, when the preliminary calculations ran, showed orbital parameters that made no sense. The eccentricity was too high, the velocity wrong for anything bound to solar gravity. The astronomer ran the numbers again, then called a colleague. Together, they watched the data accumulate across multiple nights, each observation confirming what shouldn't be possible. The object was moving through the solar system on a hyperbolic trajectory, carrying too much speed to be captured, too much momentum to belong to our sun's family. It came from outside and would return to outside, passing through our orbital space like a traveler crossing through a town on some longer journey. The realization settled slowly, like dust after a storm. Not immediate shock, but gradual understanding that something profoundly unusual was unfolding in real time. They were witnessing the arrival of only the third confirmed interstellar visitor in human history. Everything about it would need to be measured, catalogued, analyzed before it vanished back into the void. Because unlike planets that orbit predictably, unlike comets that return on schedule, this visitor would pass once and never come back. The window for observation was closing before it fully opened. Long before telescopes turned toward the void, ancient astronomers watched for travelers that moved against the fixed stars. They mapped the heavens with patience unknown to our age. The Babylonians charted Venus across clay. The Egyptians aligned their temples to stellar drift. Every culture that looked upward saw motion, rhythm, returning cycles. They called the wanderers planets, lights that refused to stay still. But beyond those familiar travelers, older texts hint at something else. Objects that appeared once and vanished forever, crossing through the known sky like messengers from distant kingdoms. The ancient observers possessed something modern astronomy sometimes forgets: in its rush toward precision. Time. They watched the same patch of sky, night after night, year after year, generation after generation. A priest might spend his entire life recording the position of a single planet, adding his observations to records maintained for centuries before his birth, knowing others would continue the work long after his death. This patience revealed patterns invisible to casual observation, the slow precession of equinoxes, the long cycles of planetary conjunctions, and perhaps, just perhaps, the rare appearance of objects that moved through the sky only once, never to be seen again. In cuneiform pressed into wet clay, scribes recorded stars with tails that appeared without warning and disappeared just as mysteriously. Unlike comets, which could sometimes be predicted, these objects arrived unexpectedly, moved strangely, and left the chroniclers uncertain whether they had witnessed omen or natural phenomenon. The distinction between the two categories barely existed in ancient thought. Everything in the heavens carried meaning. Everything that moved did so with purpose. The Vedic astronomers of ancient India tracked what they called Tumaketus, smoke-bannered visitors that crossed the sphere of fixed stars, following paths that defied the normal order. Chinese imperial astronomers recorded guest stars and broom stars, distinguishing between objects that appeared in fixed positions and those that moved across the celestial landscape. Each culture developed its own taxonomy of heavenly phenomena, but certain patterns repeated across geographical boundaries. Unexpected visitors, lights that behaved unlike anything familiar, objects that appeared from nowhere and returned to nowhere. Were some of those ancient observations actually interstellar objects, travelers from other star systems passing through during humanity's long adolescence? We will never know for certain. The records are fragmented, translated through multiple languages, interpreted through cultural filters we can barely reconstruct. But the possibility lingers that humans have been watching these visitors for thousands of years, recording them in the only language available, treating them with the reverence due to mysteries that transcended understanding. For thousands of years, those stories lived as myth, tales of fire streaking across darkness, lights that behaved unlike any star. The ancients had no word for interstellar, no concept of suns beyond their own. Yet they recorded what they saw with reverence and fear, treating each visitor as omen, each crossing as divine. Perhaps they understood something we forgot in our rush towards certainty, that the universe sends travelers, and some of them come from far beyond the family we know. Still, curiosity never sleeps. It waits. When glass lenses finally stretched human vision past its natural limits, the sky opened wider. Uranus appeared, cold and blue, proving the map was incomplete. Neptune followed, found not by sight, but by mathematics alone, a triumph of prediction over observation. Each discovery taught the same lesson. What we thought was everything was only the beginning. But even as new worlds emerged from darkness, even as telescopes grew sharper and catalogues thickened, a quiet assumption took hold. Everything that moved through our sky belonged to our sun. Comets, asteroids, planets, all born from the same ancient cloud, all bound by the same gravity. That assumption felt safe. It made the solar system a closed system, a family complete. Visitors from other stars remained in the realm of speculation, too unlikely, too distant. The mathematics said they must exist somewhere, drifting between suns in the great dark. But to actually see one, to catch it passing through our small corner of space, the odds seemed impossible. The calculations told the story clearly. Space between stars is so vast that even if rogue objects drift through the galaxy in abundance, the probability of one crossing through our tiny solar system during the brief span of human observation seemed vanishingly small. The galaxy is old. Humanity's telescope age is measured in centuries, a blink against cosmic time. For an interstellar visitor to arrive precisely when we had developed the technology to recognize it for what it was required, either extraordinary luck or something else, some factor in the equations we hadn't accounted for. Astronomers calculated the expected rate of interstellar objects passing through the inner solar system. Their estimates varied wildly, from one every few centuries to several per year. The uncertainty reflected how little we understood about the mechanisms that eject objects from their home systems. Planetary interactions could fling asteroids into interstellar space. Close encounters with neighboring stars might steal comets from their parent suns. Supernovae could scatter debris across light years. But without observational data, these remained theoretical processes with unknown frequencies. So the telescopes scanned, cataloging everything that moved, searching for the signature of something from beyond. Automated surveys photographed the same patches of sky night after night. Computer algorithms comparing images to detect any change. Most changes were known objects, asteroids in established orbits, comets on their predictable rounds. The software filtered out the familiar, leaving only the anomalies for human review. For decades, every anomaly resolved into something ordinary. A satellite glinting in unexpected sunlight, an asteroid on a previously uncharted but perfectly normal orbit, errors in the data pipeline. The systems were working, the methods sound, but the universe had not yet chosen to reveal its travelers. For centuries, no one did. Then came October 2017. Telescopes in Hawaii caught something strange, an object moving faster than gravity should allow, on a path that curved wrong. At first, they thought it was a comet. But as the data accumulated, the truth became undeniable. Its trajectory was hyperbolic, not elliptical. It wasn't orbiting the sun. It was passing through. The Pan-STARRS telescope caught it first, a faint smudge moving across the field of stars near the constellation Lyra. The automated detection system flagged it as unusual, and when astronomers examined the preliminary orbit, they realized they were looking at something that should not exist according to their prior assumptions. The object was tumbling, rotating chaotically as it moved, its brightness fluctuating wildly as different surfaces caught and reflected sunlight. Follow-up observations came quickly. Telescopes around the world turned toward the coordinates, capturing images and spectra, racing to gather data before the object moved beyond reach. It was already leaving the inner solar system when they found it, already heading back toward interstellar space. The observational window was closing fast. Every hour mattered. Every measurement added pieces to a puzzle humanity had never encountered before. They named it Oumuamua, working with Hawaiian cultural advisors to find a word that captured the significance of what they had discovered. The name meant scout or messenger, sent ahead to survey before others arrived. It felt appropriate for an object that had traveled between stars to visit our sun, the first confirmed interstellar visitor in the age of modern astronomy. For the first time in human history, we had confirmed an interstellar visitor. They named it Oumuamua, a Hawaiian word meaning scout or messenger sent ahead. The name carried weight, because if one visitor had found its way to us across the immense gulf between stars, others must be drifting out there too, silent travelers following paths millions of years old. The shape of Oumuamua proved controversial. Light curve analysis suggested it was elongated, perhaps 10 times longer than it was wide. Some models described it as cigar-shaped, others as a flat disk tumbling through space. Its unusual shape sparked speculation about its origin and nature. Natural processes could create elongated objects through collisions and gravitational stresses, but Oumuamua's extreme proportions pushed at the boundaries of what seemed plausible, and it accelerated. As the object moved away from the sun, it appeared to speed up slightly beyond what gravity alone could explain. Comets do this all the time through outgassing, jets of sublimating ice pushing them like tiny rockets. But Oumuamua showed no visible tail, no sign of the gas release that would explain its motion. The acceleration was subtle, barely measurable, but undeniable. Something was pushing it. Scientists proposed various explanations. Perhaps it was outgassing after all, but from a surface composition that didn't produce visible tails. Perhaps sunlight itself was pushing it, radiation pressure acting on its unusual shape. Perhaps its rotation and mass distribution created effects we hadn't fully modeled. Each explanation worked mathematically, but required assumptions that felt like stretching the data to fit familiar frameworks. A few researchers suggested something else, that Oumuamua might not be natural at all, that its shape, its motion, its origin from another star system pointed toward artificial construction, a probe, a derelict spacecraft, something created by intelligence rather than shaped by physics alone. The idea was controversial, widely criticized as premature and sensationalist, but it refused to completely disappear. Because once you've seen an interstellar visitor behave unlike anything natural you've encountered before, every explanation requires some form of extraordinary claim. The discovery changed everything and nothing. The universe remained exactly as vast as before, but humanity's place within it shifted slightly, from isolated family to waypoint on ancient roads. We were not alone in our orbit. We shared the solar system with travelers from elsewhere, objects born under different suns, carrying ice frozen in different dawns. Every telescope that searched the sky now carried a new question. What else is passing through that we haven't noticed yet? 2 years later, they found another. Borisov, a comet that arrived from interstellar cold with a tail that glowed like memory. Twice now, objects from beyond had crossed our threshold. Twice, the impossible had become recorded fact. Astronomers began to calculate how often such visits might occur, how many travelers pass unseen because they're too small, too dark, too far from our instruments. The numbers suggested we live in a crossroads, a place where countless paths intersect. Most of them we will never see, but some, perhaps, were meant to be seen. Comet Borisov behaved more conventionally than its predecessor. It developed a tail, outgassed predictably, showed spectral signatures consistent with comets from our own solar system. It was undeniably interstellar in origin, but it was also undeniably a comet, following rules that matched our understanding of how icy bodies behave near the sun. In some ways, this was more remarkable than Oumuamua's strangeness. It suggested that comet formation follows similar processes across different stellar environments, that the chemistry of frozen volatiles works the same way around other suns. The discovery came from an amateur astronomer in Crimea, Gennady Borisov, scanning the sky with equipment he built himself. His detection proved that interstellar visitors might be common enough that even small telescopes operated by dedicated individuals could find them. The universe was more generous with its travelers than anyone had assumed. If 2 had been found within a few years, how many more must exist? Statistical analysis began in earnest. Based on the frequency of these discoveries, astronomers estimated that several interstellar objects pass through the inner solar system every year. Most go undetected because they're faint, because they approach from directions we're not watching, because they move during daylight hours or behind the sun's glare. But they're there, a steady stream of matter from other star systems crossing through our orbital space. The realization was profound. We don't live in an isolated system. We live in a place where the galaxy itself flows through, where debris from stellar nurseries and planetary collisions and catastrophic events, light years away, eventually drifts past our worlds. Every breath of air contains atoms that once belonged to other stars. Now we knew that even macroscopic objects, rocks and ice and dust bound together, share that same interstellar heritage. We are not separate from the cosmos. We are embedded within its constant circulation. Perhaps that is why ancient astronomers watched so carefully, recording every anomaly, every light that refused to behave. They lacked our technology, but carried the same instinct. The sky holds travelers. Some announce themselves with fire. Others move in silence. And every generation inherits the same task: to watch, to wonder, to recognize when something arrives that does not belong to the family we know. For when the universe sends a visitor, it is never by accident. The question shifted from whether interstellar objects visit us to what they bring. Information, certainly. Every visitor carries data about its origin, its journey, the environments it passed through on its way here. Chemical signatures reveal the composition of the molecular cloud where it formed. Isotope ratios point toward the type of star it orbited. Surface features record bombardment by cosmic rays during its millions of years in deep space. But perhaps visitors bring something else as well. Questions that challenge our assumptions, mysteries that resist simple categorization, reminders that the universe operates according to patterns we've only begun to recognize. Each arrival forces us to expand our frameworks, to acknowledge that our models of solar system formation and dynamics were built on a sample size of 1. Now we must consider how other systems work, how they expel matter, what kinds of objects they create and lose to the galaxy. And for those who remember the old stories, who see patterns across millennia rather than just across observational data sets, each visitor carries another message: that we have been watched, that we are part of something larger, that the universe remembers us even when we forget ourselves. And in late 2024, the instruments began to tremble once more. In clay older than empires, the Sumerians wrote of gods who descended from the stars. They carved their stories into tablets that would outlast bronze and stone. Accounts of beings called the Annunaki, those who from heaven to earth came. To the priests who recorded these tales, they were not metaphor but memory, history written in the language of reverence. The Anunnaki brought knowledge, they said, writing, mathematics, the movement of celestial bodies. They taught humanity to read the sky as one reads a map, to understand that the heavens themselves were roads, and that some travelers knew how to walk them. The tablets describe a time before cities, before agriculture, when humanity lived without structure or civilization. Then the Anunnaki descended, bringing with them the tools of advancement. They taught the cultivation of grain, the domestication of animals, the organization of labor into productive systems. They established kingship, the concept that rulers derived authority from divine mandate. They created the calendar, dividing time into measurable units based on celestial cycles. Most significantly, they taught writing itself. The earliest Sumerian texts don't emerge gradually from pictographic roots. They appear suddenly, fully formed, as if the system was imported rather than evolved. The complexity suggests design, as if someone who already understood linguistic abstraction taught it to people who had never encountered the concept. Whether this reflects reality or later mythologization of a natural developmental process, the Sumerians themselves believed their writing came from beyond, a gift from travelers who knew things humanity had yet to discover. The astronomical knowledge embedded in Sumerian texts astounds modern scholars. They tracked planetary positions with precision that required generations of careful observation. They understood that celestial bodies moved in predictable patterns, that eclipses could be anticipated, that the heavens operated according to mathematical principles. Some of this knowledge seems too advanced for their technological level, as if they were recording information passed down from a source with more sophisticated tools. They described planets they shouldn't have been able to see. References to celestial bodies beyond the range of naked eye observation appear in texts thousands of years old. Some interpret these as metaphorical or religious concepts rather than literal astronomy. Others wonder if the Sumerians preserved knowledge from an earlier period when such observations had been made, knowledge they maintained even after losing the means to verify it themselves. In those ancient texts, the sky was alive with meaning. Every constellation held purpose. Every planetary alignment carried weight. The Sumerians believed the universe operated in cycles, that what had happened before would happen again, that time itself moved in circles rather than lines, and central to those cycles were the visitors, divine beings who appeared when the stars arranged themselves in specific patterns, who descended during certain celestial moments and then departed, leaving humanity to wait for the next return. The concept of cyclical return permeates Mesopotamian thought. Unlike linear historical narratives that move from past through present toward future, their worldview saw time as recursive. The same events, the same patterns, the same encounters repeated across ages. This wasn't fatalism, but recognition of rhythm. The understanding that celestial mechanics operate periodically, bringing the same alignments back after long intervals. They calculated these periods with remarkable accuracy. The Saros cycle for predicting eclipses, the precession of equinoxes over millennia, planetary conjunctions that repeated after specific numbers of years. Each cycle they measured and recorded, building a framework for understanding when certain celestial events would recur. And woven through these calculations were references to longer cycles, periods measured in thousands of years, times when the visitors would return. The tablets spoke of one world in particular, a crossing planet that followed a path unlike any other, invisible for generations, destined to return when the age turned. They marked its arrivals in their chronicles, tied them to floods and kings, to the rise and fall of cities. Whether they described an actual celestial body or something more symbolic, scholars still debate. But the conviction in those clay words feels undeniable. They believed something returned from the deep sky, and that its return marked transformation. The name they used varied across texts. Nibiru in some references, the crossing place. Marduk in others, the supreme deity who brought order to chaos. The descriptions suggest a celestial body with an elliptical orbit so elongated that it spent most of its time beyond the known planets, invisible to observation, only becoming apparent during its brief passage through the inner system. An orbit measured not in years, but in millennia. Modern astronomy finds no evidence of such a planet. Searches for undiscovered worlds in the outer solar system continue, but nothing matching the ancient descriptions has been found. The gravitational influences of known planets account for each other's motions without requiring additional massive bodies. If Nibiru exists, it must be far smaller or far more distant than the texts suggest. Or it must be something other than a planet in the conventional sense. But what if the Sumerians weren't describing a planet at all? What if they were recording visits by interstellar objects, travelers from other star systems that passed through during their civilization's long span? Objects that appeared in the sky following trajectories, unlike anything they normally observe, that brightened and faded as they crossed through, that truly did come from heaven in the sense of originating beyond their sun's domain. Reinterpreted through this lens, the ancient texts become less mythological and more observational accounts of phenomena we're only now beginning to understand ourselves. Centuries passed, the tablets crumbled or were buried, the names faded into academic footnotes. The Annunaki became mythology, stories studied but no longer believed. Until the 1970s, when a man named Zecharia Sitchin opened those ancient texts again and asked a different question. What if the Sumerians weren't speaking in symbols? What if they recorded what they actually saw? Sitchin was not an archaeologist or an astronomer, but a journalist and self-taught scholar of ancient languages. He approached the Sumerian texts without the academic frameworks that shaped mainstream interpretation, reading them as if they were straightforward historical accounts rather than mythological allegories. This perspective led him to conclusions that professional scholars found deeply problematic, but that captured public imagination precisely because they treated the ancient stories as potentially literal truth. He translated passages that mainstream academics read as poetic descriptions of divine realms and reinterpreted them as technical accounts of astronomical observations. References to heavenly abodes became orbital positions. Descriptions of divine hierarchy translated into planetary order. What scholars saw as religious mythology, Sitchin read as encoded astronomy, information about the solar system preserved in the only narrative form available to Bronze Age scribes. Sitchin claimed the Annunaki were real, beings from a hidden planet on an enormous orbit that carried it far beyond the known worlds, returning every few thousand years. He said their knowledge wasn't divine inspiration, but instruction, that they shaped early civilization because they came from a civilization far older. The academic world dismissed him. but his books spread like starlight through those who wondered if maybe, perhaps, the line between myth and history was thinner than we assumed. His hypothesis faced immediate and sustained criticism from multiple fields. Linguists disputed his translations, arguing he misread cuneiform and imposed meanings the text didn't support. Astronomers noted that his proposed planetary orbit violated basic physics and would be gravitationally unstable. Archaeologists pointed out that human civilization's development showed clear evolutionary progression rather than sudden external influence. The evidence against his literal interpretation seemed overwhelming, yet his ideas persisted. They found audiences among people who felt that conventional explanations left something unexplained, who sensed in that the ancient world knew more than modern academia credited them with. Sitchin's books offered a framework where mythology and science merged, where the gods of ancient religion were advanced beings from elsewhere in space, where human history included encounters with non-human intelligence. Whether true or not, the ideas resonated with a deep human longing to be part of something larger, to have our ancestors have witnessed wonders beyond the ordinary. The debate continues decades later, less about Sitchin's specific claims than about the broader question of how to interpret ancient texts. Should we read them purely as mythology, symbolic expressions of religious and psychological truths? Or might some accounts preserve observations of real phenomena, described in the only vocabulary available to their authors? The answer likely varies by text and context, but the question itself remains valuable. It forces us to consider what knowledge might be encoded in stories we've dismissed as mere fiction. For a generation that had already sent humans to the moon, the idea didn't seem impossible. It seemed like pattern recognition. Every ancient culture spoke of sky visitors, teachers who arrived and departed. Different names, same story. Maybe they all saw the same thing and described it in the language they had. The parallels across cultures are striking. The Sumerian Annunaki, the Egyptian Neteru, the Hindu Devas, the Mesoamerican feathered serpent, the Native American star people. Different civilizations separated by oceans and millennia, yet sharing narratives of beings who came from the sky, bringing knowledge and eventually departing with promises to return. The similarities suggest either shared psychological archetypes, cultural diffusion across great distances, or actual shared experiences of phenomena that each culture interpreted through their own framework. Mainstream anthropology favors psychological explanations. The sky naturally inspires awe. Humans across cultures looked upward and imagined the heavens populated with beings greater than themselves. The similarity of sky god myths reflects universal human cognitive patterns rather than shared historical events. We create these stories because our minds work in similar ways, not because our ancestors witnessed the same visitors. But pattern recognition works both ways. If multiple ancient cultures describe similar phenomena using different symbolic vocabularies, dismissing all of it as pure imagination risks throwing away potential data. Perhaps some myths preserve observational records in narrative form. Perhaps when cultures describe sky visitors, they're recording actual sightings of unusual celestial phenomena, objects that appeared and moved in ways that seemed intentional, that didn't fit their understanding of normal astronomical events. The challenge lies in extracting signal from noise, distinguishing between symbolic mythology and potential observational content. Most myths are clearly allegorical, teaching moral lessons or explaining natural phenomena through personification. But occasionally, texts include details that seem too specific, too technical, too precise to be pure invention. Descriptions of planetary movements, references to celestial bodies invisible to the naked eye, accounts of objects that appeared once and never returned. Modern science still writes in that same language: graphs, equations, data lines, all attempts to read the heavens. When a telescope captures something moving impossibly through our solar system, something that arrived from interstellar darkness, following a path older than stone, it's like the old priests seeing their visitors again. The names change, the instruments evolve, but the wonder remains identical. Maybe we are not discovering something new. Maybe we are remembering. The ancient observers possessed patience we've largely lost. They watched the same stars night after night, decade after decade, generation after generation, building datasets that spanned centuries. This long-term observation revealed patterns invisible to shorter timescales: the slow drift of the celestial pole, the shifting positions of seasonal star rises, planetary cycles that took decades to complete, and perhaps, occasionally, the passage of something that moved once through their sky and never appeared again. We've regained that patience through technology. Automated telescopes now monitor the sky continuously, building datasets across years and decades. Computer algorithms compare images taken nights or years apart, detecting any change, any movement, any anomaly. We've extended human observation beyond the limits of individual lifespans, creating a collective watch that never sleeps. And now, like the ancients, we're finding visitors, objects that come from beyond, that move through our space following paths we didn't predict, that carry with them evidence of realities we're only beginning to understand. The circle closes, from clay tablets to digital sensors, from eye to telescope, from myth to measurement. Humanity continues the same essential task: watching the sky, noting what moves, wondering what it means. And as the object designated 3i Atlas drifted through the solar boundary, some began to whisper that oldest name again. In quiet observatories, algorithms caught what human eyes could never see: a faint point of light moving through the outer dark, barely distinguishable from the stars behind it. The automated systems flagged it first, mathematical patterns recognizing something unusual in the data stream. When astronomers turned their attention toward those coordinates, they found an object that refused to behave like anything they knew. The initial detection came from the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of telescopes designed to find potentially hazardous objects approaching Earth. 4 telescopes spread across 2 hemispheres, scanning the entire visible sky every few nights, building a continuously updated map of everything that moves. The system discovers hundreds of new asteroids every year, most of them mundane, following predictable orbits that pose no threat. But occasionally, something unusual appears, something worth investigating further. When 3i Atlas appeared in the dataset, it showed immediate anomalies. The preliminary orbit calculation suggested an eccentricity greater than 1, meaning the object wasn't bound to the sun. Its trajectory came from a specific region of the sky and would depart toward another, not looping back, but passing through. The red flags triggered alerts to astronomers worldwide. Another potential interstellar visitor, only the third ever confirmed. Every telescope that could reach those coordinates began pointing that direction. At first, confusion. Was it a comet? An asteroid drifting inward from the Kuiper belt? The trajectory seemed wrong, the velocity too high. They calculated again, ran the numbers through different models, checked for errors. Each time, the same answer returned. The object wasn't orbiting the Sun. It was crossing through the solar system on a hyperbolic path, moving too fast to be captured by solar gravity. It came from interstellar space. The mathematics don't lie, but they require interpretation. A hyperbolic trajectory means the object has enough energy to escape solar gravity, but it doesn't reveal whether that energy came from interstellar velocity or from some acceleration within the solar system. To confirm true interstellar origin, astronomers had to trace the path backward, calculating where the object came from before solar gravity bent its course. The results showed it arriving from a direction in space with no plausible solar system source. No planet's orbit aligned to have ejected it. No known asteroid family matched its origin vector. It came from the direction of interstellar space, with the velocity of interstellar space. The conclusion felt inescapable. The realization spread quietly through the astronomical community. Another visitor had arrived, only the third ever confirmed. They designated it 3I Atlas, the third interstellar object detected by the Atlas survey system. But designation felt inadequate for what they were witnessing. This wasn't just another catalogued rock. It was a traveler from another star system, perhaps millions of years old, carrying ice frozen under skies we would never see. Professional detachment faded as the observations accumulated. Every astronomer who pointed an instrument at those coordinates felt the weight of what they were recording. This object had been traveling through space longer than human civilization had existed. It had drifted through the darkness between stars, while Earth was still inhabited only by hunter-gatherers, while the first cities were being built, while empires rose and fell. It had moved through a cosmic environment so empty that encounters with anything were measured in millions of years. And now, by mathematical coincidence or something else, it had found its way to us. Scientists traced its path backward through space, calculating where it must have originated. The trajectory pointed toward a region of sky empty of bright stars, a direction that suggested it had been wandering the galaxy for epochs beyond human memory. How long had it drifted in the cold between suns? How far had it traveled before gravity bent its path toward our small corner of the cosmos? The galactic motion calculations stretched credibility. To trace the object's path, astronomers had to account for the sun's own movement through space, the orbital velocity of our solar system around the galactic center, the gravitational influences of nearby stars, even the slight perturbations from passing molecular clouds. Each factor added uncertainty, but the overall picture remained clear. 3I Atlas had been traveling through the galaxy for at least several million years, possibly far longer. The origin direction pointed toward the Orion Eridanus superbubble, a vast cavity in space blown clear by ancient supernovae, now filled with thin gas and young stars. This region sits roughly 1,500 light-years from Earth, a distance 3I Atlas could have crossed in a few million years at its current velocity. But the uncertainty bars on that calculation stretched wide. It might have originated from somewhere within that volume, or it might have come from far beyond, its path bent by gravitational encounters we couldn't reconstruct. What star had it once orbited? Had it been ejected during planetary formation, when massive worlds migrated inward and scattered smaller bodies to interstellar space? Or had it been ripped away by a close encounter with a passing star, torn from its birth system by forces beyond its control? Or perhaps it had formed in the interstellar medium itself, condensing from the thin gas between stars, never belonging to any sun except as a temporary visitor. We may never know its true origin. The object carries no label marking its home. Its surface composition provides clues about formation conditions, but those conditions might exist around many stars. Unless we can trace its path back to a specific stellar system with absolute certainty, 3I Atlas remains a visitor whose home address is lost to time and distance. The object moved with patience, not rushing, not hesitant, simply crossing from one darkness toward another. Telescopes followed its slow progression, capturing images as it brightened slightly, developing a faint tail as solar radiation began to warm its ancient surface. It looked almost ordinary in those photographs, a smudge of light against infinite black. Yet knowing its origin transformed everything. This ice, this rock, this dust had formed around another star. It carried the signature of creation that happened somewhere else, some time else. Each image added to humanity's archive of the incomprehensibly distant, made temporarily visible. The photographs showed an elongated smudge, brighter in the center, where the nucleus reflected sunlight, fading to a diffuse glow where the tail spread into space. Standard comet morphology. Except this comet had never orbited our sun before this single passage. Every molecule of gas escaping into space, every dust particle lifted by sublimation, represented matter from another stellar environment, mixing with our solar system's inventory. Photometric measurements revealed the object was small, perhaps 2 to 3 kilometers across at most. Tiny compared to planets, modest even by comet standards. Yet it had survived millions of years in deep space without being ground to dust by micrometeorite impacts or disrupted by tidal forces from stellar encounters. Either it was younger than its journey suggested, or it was remarkably durable, protected by a surface layer of radiation-processed material that had hardened into an insulating shell. The color analysis showed it was slightly redder than most solar system comets, suggesting its surface had been exposed to cosmic rays for an extremely long time. Radiation slowly alters the chemistry of exposed ices, breaking molecular bonds and allowing atoms to recombine in different configurations. The resulting materials often absorb blue light preferentially, shifting the reflected spectrum toward red. The degree of reddening provided a rough estimate of exposure time, and 3I Atlas showed the signature of ancient surface processing. Public reaction mixed wonder with something quieter, older. For some, it was pure science, fascinating data about interstellar dynamics and planetary formation. But others heard echoes in the announcement. Another visitor from beyond. Another object crossing through our system on an impossibly long journey. In online forums and comment sections, a different conversation began. Someone mentioned the Sumerian texts. Someone else noted the timing, late 2024, a year thick with portent for those who track such things. The ancient prophecies spoke of returns, of travelers from the deep sky arriving when cycles complete. The internet age transformed how such discoveries permeated culture. Previous interstellar objects had their moment of publicity, but their significance took time to spread beyond astronomical communities. 3i Atlas arrived into a world of instant communication, where news propagated at the speed of social media, where ancient mythology and modern science could be juxtaposed in seconds. Within hours of the announcement, threads appeared connecting the discovery to every interpretation framework available. For science communicators, it presented an opportunity to explain interstellar dynamics, orbital mechanics, the nature of comets, and their formation. For Satsar conspiracy theorists, it offered evidence of everything from Planet X to alien spacecraft. For those steeped in ancient astronaut theories, it suggested the Annunaki had returned. For mainstream media, it was a fascinating but brief story, unusual enough for a few news cycles before other events pushed it aside. For humanity in general, it was another reminder that the universe was stranger and more active than our day-to-day experience suggested. Some responses showed the best of human curiosity. Children asked their parents about stars and distance, and what it meant that rocks could travel between suns. Amateur astronomers set up their telescopes, hoping to glimpse the visitor themselves. Science classes incorporated the discovery into lessons about orbital mechanics and galactic structure. For every skeptical comment dismissing it as just another space rock, several more expressed genuine wonder at the implications. And as the calculations deepened, the silence between facts began to sound like a heartbeat. It moves like memory through darkness, leaving questions in its wake. The trajectory alone defies comfortable explanation. Most comets follow predictable paths, ellipse bound to the sun's gravity, returning on schedules measured in years or centuries. But 3i Atlas follows a hyperbolic arc, one that enters our solar system and leaves without circling back. It came from outside. It will return to outside. The mathematics are clear, yet clarity does not mean understanding. Understanding requires context. We can calculate exactly where 3i Atlas will be at any future moment, but we cannot calculate what it means that it's here at all. The equations describe motion without explaining significance. They trace path without revealing purpose. And while science properly maintains that natural phenomena require no purpose beyond physics, the human mind still searches for meaning in pattern, especially when patterns align across deep time. As telescopes tracked its progression, anomalies began to surface. The object's brightness fluctuated in ways that suggested rotation, but the pattern felt irregular, chaotic. Something about its shape or composition scattered light strangely. When astronomers analyzed its spectrum, the signature looked almost familiar. Ice and rock and organic compounds, the building blocks common to comets. But the ratios seemed off, proportions that didn't quite match anything born in our solar neighborhood. The light curve showed periodicities at multiple timescales. A short period variation of about 8 hours suggested the primary rotation rate. But superimposed on that were longer period fluctuations, changes in brightness that took days to cycle through. This complexity implied either a highly irregular shape tumbling through multiple rotation axes simultaneously, or a surface with highly variable reflectivity, bright patches and dark regions arranged in patterns that created the observed signature. Computer models attempted to match the light curve to various shapes. Elongated objects rotating end over end could produce some features. Bilobed objects like two spheres touching created others, contact binaries where two separate bodies orbited while also tumbling matched certain aspects. But no single simple shape explained all the observations. Whatever Three-Eye Atlas looked like, its geometry was complex, possibly multiple components held together by weak gravity or a single body with an extremely irregular surface. The spectroscopic analysis revealed water ice as the dominant volatile, as expected for a comet. But the absorption lines showed subtle shifts from solar system standards. Deuterium to hydrogen ratios appeared elevated, suggesting formation in a colder environment than Earth's region. Trace organics showed molecular structures that didn't perfectly match the chemistry of known comets. These differences were small, requiring careful analysis to detect, but they were real. This object's chemistry reflected its alien origin. It developed a tail as it approached the inner system, a faint glow of sublimating ice responding to solar heat, normal behavior for a comet. Except the tail appeared earlier than models predicted, brighter than calculations suggested it should be, as if the object's surface responded to warmth in ways our experience couldn't fully anticipate. Perhaps ice frozen under a different sun releases differently when touched by ours. The tail's appearance at greater distance from the sun than expected suggested either higher surface activity or different ice composition than typical solar system comets. Perhaps the ices were less pristine, mixed with more volatile compounds that sublimate at lower temperatures. Or perhaps the surface structure was more porous, allowing solar radiation to penetrate deeper and warm subsurface ices that then vented through the overlying layers. Gas measurements showed the tail contained water vapor, carbon monoxide, carbon dioxide, and various organic molecules. Again, typical comet chemistry. But the ratios differed from averages. More carbon monoxide than expected, less carbon dioxide. The organic molecules included species rarely detected in solar system comets, complex carbon chains that suggested formation under different conditions. Each measurement added another small discrepancy, another hint that this visitor came from somewhere with different chemistry. The tail's behavior also puzzled observers. It showed bursts of activity, sudden brightening events where gas emission increased dramatically for a few hours before subsiding. These outbursts occurred seemingly randomly, not correlated with rotation phase or distance from the sun. Something about the object's internal structure allowed sudden releases of stored volatiles, perhaps pockets of trapped gas finding pathways to the surface as internal warming progressed. The speed troubled some observers. Moving at over 30 kilometers per second relative to the sun, faster than anything naturally born to this system could achieve without enormous gravitational assists. It carried the velocity of interstellar space, momentum accumulated across unimaginable distances. Every measurement confirmed the same truth. This was not debris from the Kuiper Belt, not a rogue asteroid shaken loose from the outer dark. It was genuinely, undeniably from elsewhere. That velocity translated to roughly 108,000 kilometers per hour, fast enough to cross the distance from Earth to the Moon in less than 4 hours. Fast enough that solar gravity, despite being immense, could only slightly bend its path rather than capture it into an orbit. The object possessed so much kinetic energy that our sun's entire mass couldn't hold it. It would pass through, get pulled slightly from its straight line course, and then continue outward at a new angle, but essentially the same speed. To put that velocity in perspective, it meant 3I Atlas had been traveling through space for roughly 1 to 2 million years to cover the distance between stellar neighbors. If it originated from a star just 5 light years away, the journey would have lasted over 50,000 years, even at this speed. And it likely came from much farther than that. The sheer patience of the cosmos revealed in that simple calculation. Objects drifting for epochs, crossing voids so empty that encountering anything required geological timescales. Yet for all its speed, 3I Atlas moved imperceptibly against the stellar background from one night to the next. Only through precise measurement could its motion be detected at all. This paradox of tremendous velocity that appeared as barely perceptible drift captured something essential about the scale of space. Distances so vast that even incredibly fast motion registered as slow creeping across the sky. Somewhere in the data, patterns emerged that felt almost deliberate. The object's path, when traced backward through the galaxy, pointed toward a region of space associated with young star systems, nurseries where worlds still form. Had it been ejected during some planetary collision millions of years ago? Was it a fragment of a world that never fully formed, cast out into the void to wander? Or something stranger still? The region it came from contained numerous young stars, many still surrounded by protoplanetary disks. These stellar nurseries are violent places where gravity collapses gas clouds into new suns and the leftover material coalesces into planets. The process involves countless collisions, ejections, and catastrophic events. Growing planets scatter smaller bodies. Close encounters between forming systems steal material. Stellar winds and radiation pressure push dust and ice outward. Much of what forms in these environments gets ejected to interstellar space, becoming the population of rogue objects that drift through the galaxy. If 3I Atlas originated in such a region, it might be quite young by astronomical standards, perhaps only a few million years old, ejected from a system still in the process of formation. This would explain why it remained relatively intact, why its surface showed only moderate radiation processing. It hadn't been wandering for billions of years like truly ancient interstellar travelers. It was a recent refugee, cast out from a system that might now be settling into stable planetary orbits while this fragment continued its eternal journey. But the youth hypothesis created its own questions. How had it been ejected with such high velocity? Gravitational scattering during planet formation typically produces escape velocities, but 3I Atlas moved faster than that. Something had given it extra momentum. A close stellar encounter, radiation pressure from its parent star during an active phase, some event more catastrophic than normal planetary dynamics. The mechanism mattered because it revealed what kinds of processes shaped the population of interstellar objects we were now beginning to detect. The debate within the astronomical community reflected older arguments. After Oumuamua in 2017, some had suggested the first interstellar visitor might be artificial, a probe or derelict spacecraft tumbling through the galaxy. The idea was controversial, widely dismissed, but never fully abandoned. Now, with 3I Atlas displaying its own collection of anomalies, those whispers returned. Not loudly, not officially, but in private conversations and late-night observations, the question lingered. What if some visitors are more than ice and stone? The argument for artificiality remained weak. Every anomaly could be explained through natural processes, even if the explanations required some stretching of parameters or invocation of conditions we hadn't previously observed. Unusual rotation, explained by irregular shape and past collisions. Strange light curves, explained by surface heterogeneity. Unexpected trajectory, explained by origin in regions we don't normally sample. Elevated activity, explained by different ice composition. The natural explanations worked. They just required accepting that our sample of comets from our single solar system might not capture the full diversity of icy bodies in the galaxy. Yet the whispers persisted because they captured something real, a sense of significance that transcended scientific measurement. Whether artificial or natural, 3i Atlas represented contact with something beyond our immediate experience. It crossed a boundary that most matter never crosses, moving from one star system to another. That journey, regardless of whether consciousness or intelligence accompanied it, marked it as special. Not just another comet, but an ambassador from elsewhere. An ambassador that spoke in the language of physics rather than words, but an ambassador nonetheless. It doesn't shimmer like a star. It absorbs light, bends it, hides within it. The telescopes catch its echo, a disturbance in the darkness, a shape that refuses to resolve completely. And yet, to those who watch long enough, it feels alive, not conscious, but intentional, as if the object remembers something we do not, a path once traveled, a destination once known. This feeling of intentionality represents pattern-seeking human consciousness, projecting meaning onto physics. The object remembers nothing. It has no awareness of its journey, no knowledge of its origin or destination. It moves according to gravity and momentum, following trajectories determined by forces it does not perceive. Yet the feeling persists among those who observe it closely, that there is something more here than random debris, something that defies complete reduction to mathematical description. Perhaps the feeling arises from recognizing our own reflection in the visitor. We too are travelers through space, riding a planet that orbits a star that moves through the galaxy. We too journey without fully understanding our origin or destination. We too respond to forces larger than ourselves. In watching 3i Atlas cross through our solar system, we witness a kindred spirit of sorts, another wanderer in the cosmic expanse, another object whose path intersects with ours briefly before diverging forever. Or perhaps the feeling arises from genuine mystery, from phenomena we observe but cannot fully explain. Science operates by reducing complexity to understandable components, but that reduction sometimes leaves residue, aspects of reality that resist complete explanation. Not because they're supernatural, but because they're incompletely understood. Every measurement of 3i Atlas produced data that fit within physics, while also hinting at complexities beneath the surface. Complexities we might never fully resolve before the object fades beyond observational reach. Tonight, the myth and the science stand side by side. The visitor, once a legend whispered in temples, now lives again in data, in light, in speculation, and somewhere beyond the orbit of Mars, it continues its crossing, silent, patient, carrying secrets from a place we will never see. The Mars reference marks its position in late 2024, somewhere in the inner solar system, close enough to be observed with moderate-sized telescopes, bright enough to be studied spectroscopically, but already beginning its outward journey. Every day carries it farther from the sun, dimmer in the telescopes, harder to track. The window for observation narrows with each passing week. Soon it will cross beyond Jupiter's orbit, then Saturn's, eventually reaching the heliopause, where solar wind gives way to interstellar medium. And then it will be gone, returning to the darkness it came from, carrying with it all the questions we couldn't answer in the brief time we shared space. Unless something changes, unless the observations reveal something so compelling that resources mobilize to send a mission, a spacecraft that could intercept the visitor before it escapes forever. The mathematics would be challenging, launch windows brief, velocity requirements extreme, but not impossible. Humanity has sent probes beyond the solar system before. We could do it again, with purpose this time, targeting a specific object of definite interstellar origin. The data such a mission could return would be invaluable. Close-up images, surface composition analysis, perhaps even a sample return if the technology allowed. We might never get another chance at an interstellar visitor moving slowly enough to reach. But such a mission requires time to plan and build, time that the visitor doesn't grant. By the time the decision could be made, designed, funded, and launched, 3i Atlas would likely be beyond reach. So for now, we watch from afar, gathering what data the distance allows, knowing we're seeing only a fraction of what there is to see. Like the ancients watching strange lights cross their sky, we record what we can and wonder about the rest. It begins with a pattern, a rhythm so faint that only mathematics can hear it. The data streams in night after night, wavelengths and magnitudes, position measurements, accurate to fractions of an arc second. At first, the readings look ordinary, like curves that rise and fall, spectral lines that shift predictably, numbers that behave exactly as numbers should. But slowly a pattern begins to form. The analysis requires patience. No single night's observation reveals anything unusual. But when datasets from multiple observatories over weeks get compiled, patterns emerge from the noise. Statistical analysis shows correlations that shouldn't exist in random data, periodicities that repeat too precisely to be coincidental, variations that synchronize across different wavelengths. The object is not behaving randomly. Something about its structure or activity produces regularity hidden beneath apparent chaos. Astronomers apply Fourier analysis, breaking down the complex light curve into component frequencies. Most comets show simple sinusoidal variations corresponding to rotation period. 3i Atlas shows multiple frequency components, some that beat against each other, creating interference patterns, others that appear and disappear depending on viewing geometry. The resulting power spectrum looks more like a musical chord than a simple tone. Multiple notes resonating simultaneously to create something richer than any single frequency alone. This complexity could result from many causes: multiple rotation axes, precession overlaying basic rotation, internal activity triggering sporadic outbursts, surface features creating brightness variations as they rotate into view. The challenge lies in disentangling which effects produce which observed patterns. Without spatial resolution to see the object's shape directly, astronomers must infer structure from how light behaves, like determining a bell's shape by analyzing the sound it makes. The object's brightness pulses, steady, rhythmic, like a heartbeat hidden in the dark. Every few hours, the intensity changes in ways that suggest something more than simple rotation. The pattern repeats with precision, as if timed by forces beyond random tumbling. Scientists trace it again and again, expecting chaos, finding instead order. Each rotation carries the same signature. Each brightening follows the same interval. The primary period of approximately 8 hours suggests rotation, the time required for the object to complete one full spin and present the same face toward Earth again. But the brightness doesn't simply rise and fall sinusoidally as expected for a rotating ellipsoid. Instead, it shows a complex profile with multiple peaks and troughs each rotation, suggesting either a very irregular shape or a surface with distinct bright and dark regions arranged in specific patterns. What creates such regularity? In natural bodies, random impacts and collisions tend to create irregular shapes that tumble chaotically. Only objects with significant internal strength or objects that have been shaped by specific processes show such ordered rotation. Rubble piles, held together by weak gravity, typically tumble unpredictably as internal components shift. Solid bodies can maintain stable rotation, but developing the specific brightness pattern observed requires particular surface features or shapes. The precision of the period also raises questions. Measured across multiple weeks, the rotation remains constant to high precision, showing no evidence of spin down or precession. Most tumbling objects in space gradually change their rotation rates through various mechanisms. Outgassing creates torques that alter spin. Tidal forces from gravity gradients affect rotation. Collisions with dust particles apply tiny but cumulative changes. The 3i Atlas maintains such stable rotation, suggests either it's very massive relative to these perturbing forces, or its rotation has already reached a stable state that resists further change. The instruments hum through the night, their sensors locked on that single point of light, crossing through the inner system. Telescopes in Chile and Hawaii track it simultaneously, comparing notes, confirming observations. What one sees, the other verifies. The pattern holds. It deepens. Every image brings new questions. Every spectrum reveals unexpected details. The global coordination of observations represents astronomy at its best. When an interesting target appears, the worldwide community mobilizes. Telescopes in different time zones maintain continuous coverage as Earth rotates. Facilities with different capabilities contribute complementary datasets. Optical telescopes measure brightness and colors. Infrared observatories detect thermal emission. Radio telescopes search for electromagnetic activity. Space-based instruments observe wavelengths blocked by atmosphere. Each contributes pieces to the puzzle. This collaborative approach proved essential for 3i Atlas. The object's faintness meant only the largest telescopes could obtain detailed spectra. Its changing position required tracking updates shared across observatories. Its limited observability window meant maximizing every clear night. Without cooperation, much of the science would have been impossible. With cooperation, humanity pooled its observational resources to extract maximum information from this rare opportunity. The data repository grew daily. Photometric measurements from dozens of observatories, spectroscopic observations spanning ultraviolet through infrared, radio telescope searches for emissions, attempts to detect polarization in reflected light. Each dataset was made publicly available within days, allowing researchers worldwide to analyze the same information to check each other's conclusions, to build understanding through collective effort rather than individual discovery. As 3I Atlas approaches its closest point to the Sun, the activity increases. The tail brightens suddenly, jets of gas erupting from the surface in bursts that seem coordinated rather than random. Outgassing, scientists call it, a normal process for comets warmed by solar radiation. Yet the timing feels deliberate, as if the object responds to warmth not through passive physics, but through something more purposeful. The outbursts show structure in both time and space. Time-resolved photometry reveals they last several hours each, rising sharply and then declining gradually as the gas disperses. Imaging shows the jets emanate from specific locations on the nucleus, bright spots that appear to be active regions responding to solar heating. As the object rotates, different regions face the Sun, and activity shifts accordingly. But the burst intensity varies beyond what simple rotation and heating should produce. Some active regions emit much more gas than others, despite receiving similar solar flux. Some remain active even after rotating away from direct sunlight. This suggests complex subsurface structure. Perhaps the nucleus contains pockets of volatile ices buried beneath less active material. As solar heat penetrates deeper, these pockets warm and pressurize until they break through to the surface in sudden eruptions. Or perhaps the surface has varying permeability. Some regions allowing gas to escape gradually, others building pressure until explosive release. Without spacecraft imaging, these remain informed speculations rather than confirmed mechanisms. The chemical composition of the jets also varied with time. Early outbursts were water-dominated. Later eruptions contained more carbon monoxide and carbon dioxide, suggesting excavation into deeper layers with different chemistry. This layering makes sense if the object formed in a protoplanetary disk where temperature gradients cause different ices to condense at different distances from the parent star. The outer layers would have formed in warmer regions, the inner layers in cold zones farther out. Warming by our Sun then peeled back these layers in sequence, revealing the object's formation history, like reading tree rings. The trajectory itself carries meaning. When astronomers trace its path backward through the galaxy, they find it originated from a region associated with stellar nurseries, places where new suns ignite and planetary systems form. It has been traveling for millions of years, perhaps longer, moving through the cold between stars with patience we cannot fully comprehend. And now it arrives here, crossing through our solar system at this specific moment, in this specific year. The galactic orbit calculations require sophisticated models. The Sun doesn't sit still in space, but orbits the galactic center at roughly 220 kilometers per second, completing one circuit every 225 million years. 3I Atlas has its own galactic orbit, different from the Sun's. To understand where it came from, astronomers must trace both orbits backward through time, accounting for how they have curved under galactic gravity, how they have been perturbed by encounters with molecular clouds and other stars. The calculations show that several million years ago, 3I Atlas and the Sun were in different parts of the galaxy. The object has since traveled across a significant fraction of the galactic disk to reach our current location. During that journey, it passed through regions of varying stellar density, crossed spiral arms where star formation actively occurs, perhaps skirted the edges of molecular clouds. Each environment left subtle signatures in its surface chemistry, tiny alterations that built up over epochs to create the complex composition now observed. That it arrives now, when humanity has just developed the capability to recognize interstellar visitors, strikes many as meaningful coincidence. For billions of years, objects like this pass through the solar system unobserved, unmarked, unrecognized. Then, in a span of just a few years, we detect three. Either the detection rate reflects our improved capabilities, finding something that was always common, or we happen to live during a period of increased interstellar traffic. The statistics favor the former, but certainty remains elusive. Some note the timing, late 2024. Others remember the ancient cycles, the prophecies of return, when certain celestial alignments complete. The comparison feels poetic rather than literal, yet the coincidence lingers. An interstellar visitor arriving during an age when humanity finally has the tools to recognize what it truly is. Not random debris, but announcement. Not chaos, but design. The year 2024 holds significance in various calendrical and astrological systems, though mainstream astronomy dismisses such correlations as numerology. Yet the human mind seeks pattern, and when patterns appear to align across disparate domains, ancient prophecy, modern astronomy, cultural anticipation, the significance feels real regardless of whether physical causation exists. This is how myths are born, how ordinary events become laden with meaning through narrative framing. From a purely statistical perspective, 3i Atlas had to arrive during some year, and any year could be connected to various prophecies and cycles through selective interpretation. The fact that it arrived in 2024 means no more than if it had arrived in any other year. Yet the human response to the timing reveals something important about how we process information, how we create meaning, how we connect present events to past stories. The science is clear. The significance is constructed, and yet the construction itself matters because it shapes how we relate to the universe we observe. In the stillness between stars, the signal deepens, and for a heartbeat, the world holds its breath. Stories like this make you look up at night. If you believe the universe still holds secrets waiting to be rediscovered, take a moment to share this journey. It began with a calculation, a simple tracing of path and origin. Astronomers mapped the object's trajectory backward through time, following its course through the spiral arm of the galaxy. Every comet leaves a trail through space, an invisible line connecting where it came from to where it arrives. For 3i Atlas, that line stretched across light years, pointing toward a region of sky the ancients once marked as significant. The backward tracing requires accounting for every gravitational influence along the path. The sun's gravity bent the trajectory inward during approach, so the true interstellar velocity was higher than currently observed. Encounters with planets would have perturbed the path slightly, each close approach adding or subtracting momentum depending on geometry. Even distant stars exert weak gravitational tugs that accumulate over millions of years. All these factors must be included to accurately reconstruct the original trajectory. The resulting calculation shows 3i Atlas approaching from the direction of the constellation Lyra in human-defined coordinates. But constellations are perspective illusions, patterns we impose on stars at vastly different distances. The actual origin region lies roughly 500 light-years away toward the galactic anticenter, an area filled with young stellar associations and the remnants of supernovae that cleared the local interstellar medium millions of years ago. This direction has been significant to humans throughout history. Various cultures assigned importance to Lyra and surrounding constellations. Vega, the bright star in Lyra, served as the pole star 14,000 years ago due to Earth's precession, making it significant in archaeological alignments. Ancient astronomers in multiple civilizations tracked this region carefully, though whether they detected anything unusual or simply found the bright stars useful for timekeeping remains unclear. The direction corresponds to constellations the Sumerians called the pathway of Anu, the Sky Father. Old star charts, carved in clay and translated centuries ago, describe this region as the origin point of divine travelers. Scholars dismissed it as mythology, poetic language for celestial observations they didn't fully understand. But when modern calculations place the interstellar visitor's origin in that same quadrant of space, the coincidence felt heavier than mathematics alone could explain. The pathway of Anu appears in Sumerian astronomical texts as a celestial band through which certain significant objects moved. Mainstream interpretation treats this as descriptive astronomy, an ancient version of the ecliptic plane where planets appear to travel. But alternative readings suggest the Sumerians distinguished between the normal planetary path and another route used by different class of objects, visitors that didn't follow regular cycles. Whether 3i Atlas actually comes from the direction the Sumerians marked as significant depends on how precisely we can align ancient and modern coordinate systems. Precession has shifted the celestial pole significantly since Sumerian times. Constellation boundaries are modern inventions that don't map cleanly onto ancient asterisms. Translation uncertainties mean we can't be completely certain which region the texts actually describe. The apparent alignment might be real, might be approximate, or might be entirely spurious. Yet the possibility resonates that ancient observers might have noted something unusual about this direction, that they might have recorded visits by objects from that region of sky, that their mythology might encode actual astronomical observation, not because gods lived there, but because ejected planetary debris from stellar nurseries in that direction happened to include objects on trajectories that eventually reached our solar system. The ancients saw the effects without understanding the mechanism and described them in the language they had. To the scientists, it means little. Space is vast. Any trajectory must point somewhere, and humanity has assigned meaning to every corner of the sky throughout history. That the object happens to arrive from a direction ancient astronomers considered sacred proves nothing except that people have always watched the heavens carefully. The alignment is statistical noise, pattern recognition in a universe too large for true patterns to hold significance. This represents the proper scientific attitude. Correlation without mechanism isn't evidence. Humans have assigned significance to virtually every celestial direction, so any object arriving from space will match someone's mythology. Unless physical causation can be demonstrated, the correlation remains curiosity rather than confirmation. Science advances by rejecting easy pattern matching in favor of mechanistic understanding. But the dismissal might be too hasty. If ancient observers did witness interstellar objects and recorded them in mythological language, those records might contain information about past visits we could verify through other means. Perhaps cometary debris from ancient interstellar visitors remains in our solar system, chemical signatures we could detect if we knew to look. Perhaps patterns in ancient observations correlate with modern simulations of galactic dynamics in ways that transcend coincidence. Science probably demands skepticism, but skepticism applied too rigidly can prevent recognition of real patterns when they exist. To others, it means everything. For those who see the universe as meaningful, as responsive, as participating in humanity's story, the directional alignment between ancient prophecy and modern discovery feels like validation. Not that the Sumerians were scientifically correct in any literal sense, but that they were observationally correct, recording something real that we've now rediscovered with better tools. This view treats ancient knowledge not as primitive superstition, but as incomplete understanding of genuine phenomena. The debate reflects deeper differences in worldview, whether reality is fundamentally meaningful or fundamentally indifferent, whether human consciousness participates in the universe or merely observes it, whether pattern recognition reflects truth or illusion. Science properly adopts the indifferent position, seeking mechanisms, not meaning. But humans are meaning-making entities, and the significance we construct shapes our relationship with reality, even when that significance has no physical force. Perhaps the synthesis lies in acknowledging both perspectives. Yes, the directional alignment is likely coincidence. Yes, meaningful universe interpretations are likely projection. But also yes, the coincidence is remarkable enough to note. And also, yes, human meaning-making is itself a real phenomenon worthy of attention. We can be rigorous scientists and wondering humans simultaneously, holding both frameworks without requiring either to dominate. The timing deepens the connection. Late 2024 marks a convergence in several ancient calendrical systems, cycles that the Mesopotamians tracked with obsessive precision. Some of those cycles measure celestial returns, periods when specific planetary alignments repeat. The mathematics work, strangely. The arrival of 3i Atlas coincides with the completion of one such cycle, a span of roughly 3,000 years since the last recorded observations of unusual celestial phenomena in Sumerian texts. The cycles in question involve long-period planetary alignments, configurations that repeat after centuries or millennia. These interested ancient astronomers because they provided a framework for organizing deep time, for connecting present observations to historical records, for anticipating future celestial events. Modern astronomy confirms these cycles exist. Planets do indeed return to similar configurations after specific intervals, though we understand them as mechanical consequences of orbital resonances rather than mystical patterns. Whether the Sumerians actually recorded anything 3,000 years ago that corresponds to interstellar visitor observations is unclear. Their astronomical diaries are fragmentary. Translation uncertainties complicate interpretation. The texts that survived were copied and recopied across centuries, with each scribe potentially introducing modifications. What seems like a record of unusual phenomena might be later interpolation, myth inserted into historical chronicles, or metaphorical language describing religious concepts rather than celestial observations. But if we grant the possibility that some records are genuine observations, then the timing becomes interesting. 3,000 years is long enough that direct cultural memory wouldn't persist. long enough that only written records could preserve knowledge of events from such distance, yet short enough that some ancient civilizations did maintain continuous records across such spans. The coincidence of that time interval and the arrival of 3i Atlas during its completion invites speculation even while resisting confirmation. Perhaps coincidence, perhaps memory encoded in orbit and time. The difference between the two explanations requires faith in one direction or skepticism in another. What remains undeniable is the precision. The object didn't arrive randomly. Its path, calculated across millions of years of drift through interstellar space, brought it through our solar system at this exact moment. Gravitational perturbations from other stars, the gentle tug of galactic rotation, countless tiny influences shaped its journey. And somehow, all of those forces aligned to deliver it here, now. The precision is real, but its significance isn't. Yes, 3i Atlas arrived in late 2024, but it had to arrive during some specific time, and that time would coincide with various human calendrical milestones simply because humans have created countless calendars and cycles. The object's arrival is precisely dated, but that precision is observational, not meaningful. We can state exactly when it passed through our solar system. Whether that when matters beyond the measurement itself remains philosophical rather than scientific question. Determinism guarantees precision without implying purpose. Every physical event happens at an exact time for exact reasons. Gravity doesn't approximate. Orbital mechanics don't round off. The universe operates with perfect precision at all scales. That 3i Atlas arrived when it did reflects the accumulated gravitational influences of millions of years playing out according to physics. The timing is as precise as it is meaningless in terms of human significance. Unless consciousness and cosmos interact in ways physics hasn't yet formalized. Unless meaning is a real force, even if unmeasurable. Unless the universe does pay attention to the observers arising within it. These possibilities remain outside science's domain while remaining central to human experience. We can acknowledge both the scientific fact of meaningless precision and the human experience of meaningful coincidence without requiring contradiction. Some call it pathfinding. The idea that 3i Atlas is not destination but announcement, a marker indicating that something follows behind. In ancient texts, scouts preceded larger arrivals. The first light meant others approached in darkness. Whether such interpretation holds any reality matters less than what it reveals about human nature. We see patterns, we assign meaning, we remember old stories and search for their echoes in new data. The Pathfinder metaphor captures how humans think about sequences. One event suggests others will follow. A scout implies an army. A messenger implies a message. We build narratives from isolated data points, connecting them into stories that make sense of otherwise random occurrences. This tendency serves us well in social contexts where actions do often signal intentions, but it can mislead us in physical contexts where events occur without purpose or prelude. Is 3i Atlas a pathfinder? Not in any intentional sense. It carries no awareness of following objects. It communicates nothing to them. It marks no route for later travelers. It simply is, an object moving through space according to physics. If other interstellar visitors follow, they do so independently, following their own trajectories determined by their own histories. The sequence is coincidence, not coordination. And yet the metaphor might be accidentally accurate. If the rate of interstellar visitor detection is increasing because our capabilities are improving, then 3i Atlas is indeed a pathfinder in the sense that its detection path helps us find others. Each discovery teaches us what to look for, what trajectories to monitor, what characteristics distinguish genuine interstellar objects from solar system natives. In this functional sense, early detections do scout for later ones, marking the territory not for future visitors, but for future observations. The world looks up again. What was once dismissed as legend now moves across our telescopes, slow, deliberate, patient. As the object passed its closest approach to the Sun and began its journey back toward interstellar space, it left something behind. Not debris, but disturbance. Across the orbital paths, something subtle has changed. In the weeks following the visitor's passage, instruments detected faint perturbations in the solar wind, ripples in the electromagnetic field that flows outward from the Sun. Small variations, barely measurable, yet consistent, as if the object's passage bent space itself slightly, leaving an impression that lingers after the traveler moves on. The solar wind consists of charged particles streaming outward from the Sun's corona at speeds of hundreds of kilometers per second. This plasma carries the Sun's magnetic field lines into interstellar space, creating the heliosphere that shields the inner solar system from galactic cosmic rays. Any object moving through the solar wind disturbs it, creating a wake similar to a boat moving through water, but governed by plasma physics rather than fluid dynamics. 3i Atlas created such a wake, a region behind it where the solar wind density and velocity differed slightly from undisturbed flow. Spacecraft designed to monitor space weather detected this disturbance as the object passed. The measurements were subtle, requiring careful analysis to separate the signal from natural solar wind variability. But once identified, the wake persisted for days after the object itself had moved on, gradually dissipating as the faster solar wind flow filled in the disturbed region. What made this interesting was the wake structure. Most objects create simple wakes, depleted regions directly behind them, where their presence temporarily blocked the solar wind. But 3i Atlas's wake showed complexity, variations in density, and magnetic field orientation that suggested interaction beyond simple blockage. Perhaps outgassing from the comet's surface injected fresh ions into the solar wind, creating local enhancements. Perhaps the object's rotation created rotating features in the wake. Perhaps multiple active regions on different parts of the nucleus created a complicated source distribution. The exact mechanism remained unclear, but the effect was measurable. Scientists measured the plasma density in the object's wake. Where it passed, charged particles behaved differently for a brief window, aligning in patterns that suggested an influence beyond simple gravitational pull. The effect dissipated quickly, smoothed away by the vast currents of solar radiation. But for those few days, something remained, a signature in space, invisible to the eye, clear to the numbers. Plasma physics in space creates phenomena unfamiliar from everyday experience. Magnetic fields can trap and guide charged particles. Density variations can trigger instabilities that propagate as waves. Different ion species respond differently to electromagnetic forces, creating separation and structure. All of these effects played out in the wake behind 3i Atlas, creating a temporary laboratory where natural plasma processes could be observed and measured. The measurements contributed to understanding of how comets interact with the space environment. Most studies of such interactions involve comets from our own solar system, which might have different properties than interstellar visitors. Does ice formed under a different sun outgas differently? Do different formation conditions create different surface structures that affect how solar wind couples to the nucleus? The 3I Atlas observations suggested, yes, subtle differences exist, adding another data point to our understanding of cometary diversity. Gravity is patient. It doesn't shout. It waits. The object's mass, whatever it truly carried, warped the fabric of space around it as it moved, not dramatically, not like a planet or star, just enough to tug at passing dust, to bend the trajectory of smaller debris by fractions of a degree. Astronomers catalogued these tiny deflections, mapping how the visitor's presence altered the motion of particles in its vicinity. Each deviation told a story of unseen forces, of mass pulling at emptiness until emptiness responds. Einstein taught us gravity isn't a force, but a curvature of space-time. Massive objects bend space around themselves, and other objects follow the straightest possible paths through that bent space, creating what we perceive as gravitational attraction. Even small masses create measurable curvature, though detecting it requires sensitive instruments and careful analysis. Did 3I Atlas's gravity detectably affect anything? Perhaps. If the object passed close to the orbit of known asteroids, its gravitational pull would have slightly altered their trajectories. These changes would be tiny, measured in meters of position shift after months or years, but potentially detectable through careful orbit monitoring. Such measurements could constrain the visitor's mass more accurately than brightness estimates alone, providing another piece of the physical characterization puzzle. More interesting would be detecting gravitational effects on the solar wind or interplanetary dust. These particles move fast enough that gravitational deflection is minimal, but not zero. A plasma stream passing near 3I Atlas would bend slightly toward it, creating a gravitational focusing effect downstream. Dust particles on intersecting trajectories would be pulled slightly off course. These effects would be incredibly subtle, buried deep in the noise of natural variability, but they represent real physical phenomena that could in principle be measured with sufficiently precise instruments. Some observations proved harder to explain. Radio telescopes detected brief bursts of electromagnetic activity that seemed to emanate from the region near the object. Natural processes, scientists suggested, interactions between the comet's ionized tail and the solar magnetic field. But the timing of those bursts matched no known model. They arrived in clusters, separated by regular intervals, almost rhythmic, almost like pulses. Radio emission from comets is well documented, but not fully understood. The basic mechanism involves solar wind interaction with the expanding gas cloud around the nucleus. The solar wind carries magnetic field lines that get draped around the obstacle created by the comet's atmosphere. Ions in the atmosphere get accelerated by electromagnetic fields, producing radio waves as they spiral along field lines. The process is complex, involving plasma instabilities, shock formation, and particle acceleration. Most cometary radio emission is broadband and irregular, reflecting the turbulent nature of the underlying plasma processes. But occasionally, comets produce narrowband emissions or quasi-periodic bursts, suggesting more organized activity. These events are poorly understood, but might involve periodic modulation by the nucleus rotation, or standing wave patterns in the plasma environment, or other structured phenomena. 3I Atlas's radio behavior added to the puzzle. The detected bursts occurred at irregular intervals, sometimes hours apart, sometimes clustered within minutes. Each burst lasted seconds to minutes, showing rapid onset and slower decay. The radio spectrum peaked in the low MHz range, typical for solar-wind interaction regions, but the burst timing didn't correlate obviously with any measured property. Not rotation period, not outburst timing, not solar wind conditions. The activity seemed autonomous, driven by internal processes rather than external forcing. To understand it, researchers had to slow down, to feel the rhythm, rather than calculate it. Each measurement revealed layers beneath the surface interpretation. What appeared random at first glance showed structure when examined closely. The wake wasn't chaos. It was complexity, patterns within patterns, information encoded in the subtle disturbance of space itself. This shift from analysis to contemplation marks where science approaches its limits. The data is real. The measurements are accurate. The phenomena are physical. But comprehension requires something beyond calculation, an intuitive grasp of systems too complex for simple equations. The researchers studying 3I Atlas found themselves describing their subject in language that felt almost mystical. Not because anything supernatural was occurring, but because the natural processes at play exceeded easy description. Complex systems science teaches that pattern can emerge from simplicity through nonlinear interactions. Chaos theory shows how deterministic systems produce unpredictable behavior. These frameworks help understand phenomena like turbulence, weather, brain activity, systems where knowing all the rules doesn't enable prediction of all the outcomes. Perhaps the electromagnetic environment around 3I Atlas operated in this regime, where underlying physics was simple, but resulting behavior was complex beyond tractable calculation. Perhaps that's what makes interstellar visitors so compelling. They don't announce themselves loudly. They pass through silence, leaving only whispers behind. And in those whispers, we hear what we're prepared to hear. Data, some say. Memory, others reply. The difference depends on whether you believe space itself can remember the shapes that move through it. The philosophical question of whether space remembers is metaphorical but points at real physics. Do transient events leave permanent marks? At quantum scales, yes. The universe retains information in ways that violate classical expectations, leading to concepts like quantum entanglement and information conservation in black holes. At macroscopic scales, the answer is murkier. Most disturbances dissipate, information spreading and diluting until recovery becomes practically impossible, even if theoretically preserved. Yet something remains. The wake behind 3I Atlas dissipated, but the particles it disturbed carried that history forward in their altered trajectories. The gravitational deflections it imparted persist in the orbits of affected objects. The light it reflected toward Earth reached our detectors and was recorded, creating permanent records of its passage. In these senses, space does remember, not through any mystical consciousness, but through the physical consequences of events that propagate forward in time. The data keeps arriving, endless lines of numbers, all whispering the same truth. Something unseen shaped everything it touched. If stories like this remind you how fragile and yet how infinite our place in the universe truly is, leave a like. It helps these cosmic mysteries travel farther, like ripples through the same space we seek to understand. Between the stars, light carries more than illumination. It carries origin. Every photon that leaves the surface of 3I Atlas began its journey in darkness, frozen within ice older than human memory. As solar radiation warmed that ancient surface, molecules broke free, releasing light that had been trapped since the object's formation. That glow reached Earth carrying information about composition, about temperature, about the distant place where this traveler was born. Light tells everything if we know how to listen. Each wavelength absorbed or reflected reveals chemical bonds. Each shifting spectrum shows motion and temperature. Each polarization pattern hints at surface texture. The photons that traveled from 3I Atlas to our telescopes crossed space as information carriers, messengers in the truest sense, bringing news from elsewhere. The process begins with the sun. Solar photons strike the comet's surface, some absorbed and converted to heat, others reflected. The reflected light carries the signature of what reflected it. If ice dominates the surface, the reflection is strong in visible wavelengths. If organic compounds coat the ice, reflection weakens and shifts toward red. If dust covers the surface, reflection becomes diffuse and wavelength dependent in complex ways. By analyzing the color and brightness of reflected light, we infer surface properties. But reflection is only part of the story. The absorbed solar energy heats the surface, causing ices to sublimate. The escaping gas absorbs and re-emits light at specific wavelengths determined by molecular structure. Water vapor shows strong absorption lines in the ultraviolet and infrared. Carbon monoxide has distinct features in the infrared. Organic molecules produce complicated spectra across many wavelengths. By observing which wavelengths are absorbed or emitted, we identify which molecules are present. Spectroscopy revealed the signature. Water ice, carbon compounds, traces of ammonia and methane. The chemistry of comets, familiar yet subtly different. The ratios suggested formation conditions unlike those in our solar system. Temperatures and pressures that belonged to another stellar nursery. Light translated those differences into wavelengths, colors that told stories of alien dawns. The water detection was straightforward. Strong absorption bands were expected. But the details mattered. The spectrum showed both crystalline and amorphous ice signatures, suggesting the surface had been processed by heating or radiation. The deuterium to hydrogen ratio, measured through fine spectroscopic analysis, was slightly elevated compared to solar system averages, hinting at formation in a colder environment or under different conditions of nucleosynthesis. Carbon compounds appeared in various forms. Carbon monoxide ice, detected through infrared absorption. Carbon dioxide, both frozen and gaseous. Organic molecules containing carbon-hydrogen bonds showed up as broad features across multiple wavelength regions. Some of these organics were familiar from solar system comets, simple alcohols, aldehydes, nitriles. Others were less common, complex molecules that suggested rich chemistry, either during formation or during the long interstellar journey. The presence of ammonia and methane, though detected only in trace amounts, was significant. These volatiles are even more fragile than water ice, sublimating at lower temperatures. Their survival suggested either they were protected within the nucleus interior, or they had been replenished somehow during the object's journey, or formation conditions favored their retention more than typical solar system environments. Each possibility pointed toward differences in the formation environment. Light has memory, even if we do not. Each beam that travels from the object to our telescopes crosses millions of kilometers in minutes, carrying a record of what it touched, what reflected it, what changed its path. When astronomers analyzed those beams, they found more than expected. Polarization patterns that suggested complex surface structures, brightness variations that hinted at irregular rotation or multiple components traveling together. Polarization measures the orientation of light's electromagnetic oscillations. Unpolarized light oscillates in all directions perpendicular to its travel, but reflection from surfaces, scattering by particles, or emission from asymmetric molecules can create preferential orientations, polarizing the light. By measuring polarization across wavelengths and observing angles, we infer properties of the scattering or reflecting material. 3i Atlas showed moderate polarization that varied with rotation phase. When certain surface regions faced Earth, polarization increased, suggesting those regions had different texture or composition. The polarization degree and wavelength dependence matched models of surfaces covered with irregular dust particles, consistent with a comet nucleus mantled by sublimation residue. But the variations across rotation suggested some regions were more dust-covered than others, perhaps indicating areas of active sublimation exposing fresher ice. The brightness variations carried additional information. The light curve's shape changed subtly at different wavelengths. Measurements in blue light showed slightly different periodicities than measurements in red. This wavelength dependence indicates color variations across the surface, some regions more reflective in blue, others in red. Since ice is typically neutral in color, while organic compounds and irradiated materials are red, these variations map the distribution of different surface materials as they rotate into and out of view. The tail itself became a study in luminescence. As gas escaped the warming nucleus, it caught sunlight and glowed, painting a faint streak across the darkness. But unlike typical comet tails, this one showed fluctuations, brightenings that came and went in pulses. Solar-wind interaction, scientists explained, variations in outgassing rates, yet the pattern felt too regular, too timed, as if the object released its breath in measures. Cometary tails glow through two processes. Dust particles reflect sunlight, creating a yellowish dust tail that curves along the comet's orbit due to radiation pressure. Gas molecules fluoresce when solar ultraviolet light excites their electrons, creating a bluish ion tail that points directly away from the sun along magnetic field lines. Most comets show both, with varying relative brightness, depending on dust-to-gas ratio and activity level. 3i Atlas's tail showed predominantly fluorescence, indicating gas-rich emission. The brightness variations correlated with outburst events detected in other measurements, confirming they represented real changes in activity level. But superimposed on these irregular variations was a subtler periodic modulation, a gentle brightening and dimming at the rotation period. This suggested active regions on the nucleus that vented gas preferentially when facing the sun, creating a rotating pattern of emission intensity. The tail's chemical composition evolved during observation. Early spectra showed water-dominated emission lines. As perihelion approached and the object warmed, carbon monoxide lines strengthened. Post-perihelion, as the object began receding, water returned to dominance, while more exotic species like sulfur compounds appeared briefly. This temporal evolution mapped how solar heating penetrated into the nucleus, accessing different layers with different chemistry. Perhaps that's what makes light from interstellar space so compelling. It doesn't just show us what exists, it shows us what remembers. Every wavelength carries the imprint of its journey, bent by gravity, scattered by dust, changed by every interaction across the void. By the time it reaches our instruments, that light has become a message, written in a language we're still learning to read fully. The photons detected from 3I Atlas began their journey at various points in time and space. Some reflected directly from the nucleus, traveling straight from Sun to comet to Earth in minutes. Others scattered through the expanding gas cloud, delayed by microseconds and shifted in wavelength by the Doppler effect of moving gas. Still others absorbed into molecules and re-emitted after energy cascaded through excited states, carrying information about molecular structure rather than just surface properties. Each photon is a messenger, but the message requires interpretation. The raw light conveys information, but extracting meaning requires models of how light interacts with matter, calibrations that account for instrumental effects, statistical analysis to separate signal from noise, physical reasoning to infer causes from effects. The process is translation, converting photons into knowledge through layers of interpretation built on centuries of accumulated understanding. Yet something transcends the technical process. The light from 3I Atlas traveled across space to reach us, connecting the there and then to the here and now. That connection is real and physical, not metaphorical. The photons that entered our telescopes had previously interacted with matter from another stellar system. In detecting them, we touched, however remotely, something from elsewhere. The light is both data and connection, information and relationship. Ancient cultures interpreted celestial light as divine communication. Modern science calls it electromagnetic radiation. Both approaches recognize the same truth. Light connects what is distant. It makes the invisible knowable. When photons from 3I Atlas strike our detectors, they complete a journey that began in another stellar system, perhaps around a sun we cannot see, in an epoch before Earth had oceans. The ancients lacked our understanding, but possessed the same sense of connection. They watched lights in the sky and felt themselves part of something larger, participants in cosmic patterns beyond immediate comprehension. Modern instruments give us detail the ancients lacked, but we're engaged in the same essential activity, watching light from afar and seeking meaning in its patterns. Perhaps this continuity matters more than the technical details. Humans have always looked upward, always wondered at lights in the darkness, always sought to understand their place in the cosmos. The tools change, the knowledge deepens, but the fundamental posture remains constant. We are watchers of light, interpreters of signals, seekers of connection with realities beyond our immediate experience. The universe reflects attention. Every time we point our instruments toward the dark, something answers in light. There comes a point where knowledge becomes reflection. The equations that once held certainty begin to blur at the edges. Numbers start to feel less like answers and more like questions written in another language. Astronomers, trained in mathematics and physics, find themselves reaching for words they never expected to use. Mystery, wonder, the ineffable. It is science wrapped in humility, the recognition that some phenomena resist complete understanding, no matter how precise the instruments become. This transformation occurs gradually. Early in a research program, problems yield to analysis. Data fits models. Observations match predictions. The universe behaves as equations suggest it should. Success builds confidence that understanding is deepening, that mysteries are solving, that the path toward complete knowledge is clear. But with sufficient time and attention, complexity emerges. Edge cases appear where models struggle. Anomalies accumulate that resist simple explanation. The system reveals layers beneath the initially understood surface. What seemed like complete description proves to be useful approximation, adequate for many purposes, but insufficient for others. The researcher realizes their understanding is partial, their equations incomplete, their framework limited. This realization can be painful. After years mastering a technical domain, discovering its limits feels like failure, but it's actually progress. The simple problems were solved long ago. What remains is genuinely difficult, perhaps fundamentally so. Reaching the edge of understanding means standing at the frontier, the place where knowledge gives way to mystery, where the next discoveries await, but their nature remains unclear. For centuries, we built models of the universe that worked. Gravity explained orbits. Spectroscopy revealed composition. Mathematics predicted motion. Every mystery eventually surrendered to patient observation and careful calculation. But interstellar visitors like 3I Atlas remind us that explanation and comprehension are not the same thing. We can measure the object's trajectory perfectly while understanding nothing of what it means to travel between stars for millions of years. We can analyze its chemistry without grasping what it signifies that such chemistry formed elsewhere, around another sun. The measurements are precise. Trajectory known to high accuracy. Composition catalogued in detail. Physical properties constrained within narrow ranges. By scientific standards, 3I Atlas is well characterized. We know what it is, where it came from, where it's going. The data is comprehensive. But comprehension requires something beyond data. What does it mean that this object exists, that it traveled so far, that it arrived here now? These questions aren't answered by better measurements or more sophisticated models. They're questions of meaning, significance, context. They require philosophical reflection rather than empirical investigation. And scientists, trained to avoid such questions as outside their domain, find themselves compelled toward them anyway, because the phenomenon itself demands it. The great minds of our age speak like the priests of old when facing such encounters. They describe phenomena that sound like myth, objects that move through darkness carrying messages we cannot fully decode, patterns that repeat with purpose we cannot confirm, light that remembers, space that listens. The language shifts because the reality demands it. Maybe those ancient astronomers who assigned divine meaning to celestial events weren't being primitive. Maybe they were being honest about the limits of human comprehension. Consider how the best science communicators describe 3I Atlas. They don't just recite facts and figures. They tell stories. They use metaphor. They invoke wonder. A traveler from the stars, a messenger from the deep, a visitor carrying secrets from the cosmic dawn. This poetic language isn't fluff or dumbing down. It's an honest attempt to convey significance that transcends technical description. When Carl Sagan spoke of being star-stuff contemplating stars, he merged poetry and astronomy into something more powerful than either alone. When Neil deGrasse Tyson describes feeling connected to the cosmos, he's making a spiritual statement grounded in physical fact. When researchers describe the eerie precision of 3-eye Atlas's patterns or the mysterious nature of its emissions, they're not abandoning scientific rigor. They're acknowledging that precision and mystery coexist, that we can measure everything and understand very little. Ancient priests faced the same challenge. They observed celestial phenomena carefully, recorded them precisely, and then struggled to express what those observations meant. Their frameworks included God's and divine will, because those were the available explanatory tools. We're more sophisticated in our mechanisms, but no less mystified by significance. Different vocabulary, same fundamental position, at the edge of knowledge, wondering what lies beyond. When the data aligns too perfectly with old myths, when an interstellar visitor arrives from the direction ancient texts marked as sacred, when the timing coincides with cycles measured in clay, the line between science and spirituality fades. Not because one is right and the other wrong, but because both approach the same horizon from different paths. One uses telescopes and spectrographs. The other uses story and symbol. Both reach toward truth that exists beyond either method's grasp. This convergence frustrates those who insist on strict boundaries between domains. Science, they argue, deals with measurable reality. Spirituality deals with subjective experience. Mixing them creates confusion. Perhaps, but reality doesn't respect our categorical boundaries. Some phenomena genuinely sit at intersections, accessible to multiple modes of inquiry, yielding partial truths to each, while withholding complete truth from all. 3-eye Atlas is such a phenomenon. The physical reality is measurable and measured. The trajectory is calculated. The chemistry is analyzed. These are facts, but the significance is interpreted. The meaning is constructed. The wonder is experienced. These are equally real, even if less objective. A complete account must include both. Pure physics describes what happened, but it doesn't touch why it matters, why humans care, why the discovery resonates across cultures and worldviews. The ancient myths weren't wrong in their core insight, that the cosmos contains wonders that transcend human scale, that mysterious visitors sometimes arrive from beyond, that patterns in the heavens might signify things we don't fully understand. The myths were wrong in their mechanisms, attributing to gods what physics accomplishes without intention. But the sense of mystery, of significance, of connection to something vast, those responses were and are appropriate. The universe is genuinely awesome. Pretending otherwise for the sake of scientific detachment misses something essential. Perhaps science is not discovering, but remembering. Perhaps the universe has always operated according to principles we glimpse only partially. Principles that ancient cultures encoded in mythology because they had no other vocabulary. The Sumerians spoke of sky travelers and return cycles. Modern astronomy speaks of interstellar objects and orbital mechanics. Different words, same wonder. Same attempt to make meaning from motion we witness but cannot fully explain. This idea of remembering rather than discovering resonates across cultures. Many wisdom traditions teach that knowledge exists eternally, that learning means recovering what was always true rather than creating new understanding. Plato's theory of recollection, Hindu concepts of eternal Vedic knowledge, Buddhist ideas of rediscovering what Buddha nature already knows. These frameworks treat discovery as recognition, learning as remembering. Applied to science, the metaphor suggests the patterns we find were always present, the laws we formulate always operated, the structures we uncover always existed. We aren't inventing physics, we're recognizing it. In this sense, modern astronomy remembers what reality always was, just as ancient astronomy remembered it through different frameworks. The universe hasn't changed. Our ability to perceive it has deepened. And if ancient observations recorded genuine phenomena in mythological language, then we're literally remembering, recovering knowledge that was once possessed, was lost or obscured, and now returns in new form. The Sumerians watched the sky and recorded what they saw. We watch the same sky with better tools and record what we see. If both data sets describe real phenomena, then we're continuing a conversation begun thousands of years ago, adding new vocabulary and precision, but addressing the same fundamental questions. At the edge of science, silence takes over. The data stops providing answers and starts providing awe. And all that remains is the question that has driven every stargazer since humans first looked up. What lies beyond our understanding? If stories like this make you feel that echo, that quiet pull to keep wondering, share this journey with someone who listens to the same night sky. There are things that should not exist, yet do. For years, interstellar visitors were theory, mathematical possibilities that lived in equations but never materialized in telescopes. The distances were too vast, the odds too small. Then Oumuamua arrived, then Borisov, and now 3I Atlas, crossing through our solar system, carrying ice from another star, moving on a path millions of years old. It defies the comfortable assumption that our corner of space remains isolated. It proves the universe still creates encounters we never predicted. The shock of the impossible made routine has a particular quality. Initially, each interstellar visitor generated surprise, wonder, extensive analysis. Oumuamua was front-page news worldwide. Borisov received significant attention, though less than its predecessor. Now 3I Atlas, while still noteworthy, generates less shock because the category interstellar visitor has become established. We went from never seeing such objects to expecting them, all in the span of a few years. This normalization is simultaneously progress and loss. Progress because we've updated our understanding to match reality. The solar system is not isolated but porous, permeable to travelers from elsewhere. This knowledge corrects previous misunderstanding. But loss because each successive visitor feels less miraculous, less impossible, more like another data point in an expanding catalogue. The wonder diminishes as familiarity grows, yet wonder should not diminish. Each visitor remains remarkable, even as the category becomes recognized. That 3I Atlas traveled millions of years to reach us is no less extraordinary than Oumuamua's journey. That it carries ice frozen around a different sun remains profound regardless of how many other such objects we eventually detect. The universe's generosity in sending us these travelers should inspire perpetual awe, not habituated acknowledgement. Perhaps the challenge is maintaining beginner's mind, approaching each phenomenon with fresh wonder despite growing expertise. Zen practitioners cultivate this quality deliberately, seeking to experience reality directly rather than through conceptual filters built from past experiences. Scientists might benefit from similar practice. Yes, understand the physics. Yes, build the models. But also pause to genuinely appreciate the astonishing nature of what those models describe. What makes this visitor different is not just its origin. Other interstellar objects pass through quickly, barely warming before they vanished back into the void. But 3-Eye Atlas arrived with anomalies that resist easy explanation. The brightness fluctuations, the trajectory alignment with ancient astronomical coordinates, the timing that coincides with prophetic cycles. Each detail alone means little. Together, they form a pattern that feels less like coincidence and more like convergence. Convergence is the right word. Multiple threads coming together, ancient observation and modern detection, mythological framework and scientific measurement, expected physics and anomalous behavior, random chance and meaningful timing. None of these convergences proves anything beyond their own occurrence, but their simultaneous presence creates a gestalt, an overall impression that transcends the sum of individual facts. Human brains are pattern recognition engines evolved to detect signal in noise. This capability serves us well in navigating complex environments, but can misfire, finding patterns where only randomness exists. Faces in clouds, agency in coincidence, meaning in noise. Skepticism about apparent patterns is usually warranted. Most patterns we perceive are indeed spurious, but not all. Some patterns are real. Some convergences reflect actual underlying connections. The challenge lies in distinguishing true pattern from false positive. Science provides methodologies for this: statistical testing, mechanistic investigation, repeatability assessment. But those methodologies work best for patterns that recur frequently enough to study systematically. For unique events, like the arrival of 3-Eye Atlas, statistical approaches offer limited guidance. We're left with judgment, intuition, and the uncomfortable acknowledgement that certainty is unattainable. To observe it is to look at something that has never known Earth's warmth, never seen our sun except as a distant point of light, and yet somehow found its way here. It endures across epochs we cannot fully imagine, silent, patient, carrying within its frozen structure the signature of creation that happened elsewhere. The impossible made visible. The endurance matters. 3-Eye Atlas has existed for millions of years at minimum, possibly far longer. During that span, it experienced conditions so hostile that survival seems implausible. Cosmic ray bombardment that should have shattered molecular bonds, micrometeorite impacts that should have ground it to dust, thermal stresses from passing near stars, tidal forces during stellar encounters. Yet it remained intact, coherent, recognizable as a comet rather than diffuse debris cloud. What allows such endurance? Perhaps 3-Eye Atlas is larger than estimates suggest, mass and gravity sufficient to hold itself together despite perturbations. Perhaps it's unusually dense, compacted by its formation conditions into structure more resilient than typical comets. Perhaps it's younger than its journey distance implies, ejected from a nearby system more recently. Or perhaps comets are simply more durable than we've assumed. Our understanding built on solar system examples that haven't survived the rigors of deep space transit. The endurance also speaks to patience at cosmic scale. No rushing toward destination, No urgency in the trajectory, just steady movement across unimaginable distances at speeds that seem fast by human standards, yet are glacially slow against astronomical scales. To maintain such constancy for so long suggests universe operating by principles far removed from human experience of time and purpose. In ancient texts, the Annunaki were not conquerors, but teachers, beings who arrived from the stars to guide humanity toward knowledge. Whether those stories describe literal visitors or symbolic wisdom matters less than what they reveal about human longing. We want the universe to remember us. We want our questions to be met with answers from beyond. And when an object arrives from interstellar space following paths the ancients marked as sacred, we cannot help but wonder if maybe the return was never meant to be invasion. Maybe it was meant to be reminder. The teacher motif appears across cultures and myths. Prometheus bringing fire, Thoth teaching writing, Quetzalcoatl instructing in arts and sciences. These stories express a deep human intuition that knowledge comes from beyond ourselves, that we were lifted from ignorance by forces or beings greater than us. Whether these myths encode historical encounters with advanced civilizations, or whether they're symbolic expressions of how culture and knowledge accumulate and transmit across generations, they speak to our sense that wisdom is received, not just invented. Applied to Three-Eye Atlas, the teacher interpretation suggests the universe itself instructs through phenomena. Each interstellar visitor teaches us that our models were incomplete, that reality exceeds our expectations, that mysteries remain. The teaching isn't intentional. The universe doesn't care whether we learn, but it's real nonetheless. We grow through encounter with phenomena that challenge our understanding. Three-Eye Atlas is teaching us about interstellar dynamics, about cometary diversity, about the permeability of stellar systems. The teacher role requires no consciousness, only the presence of something we didn't expect to find. The reminder interpretation goes deeper. Perhaps we've encountered such visitors before in humanity's deep past, and the current detections are re-encounters rather than first contacts. Perhaps the myths preserve memory of previous passages described in the language available at the time. Perhaps Three-Eye Atlas arrives not to teach something new, but to remind us of something old, knowledge we possessed but forgot. This reading treats ancient astronomy as continuous with modern, different methods toward the same phenomena. The object exists precisely because we needed something to challenge our certainty. It moves through our solar system not to threaten, but to teach the oldest lesson. That wonder outweighs knowing. That mystery is not absence of truth, but presence of depth we have yet to reach. Every distant traveler, every impossible arrival reminds us how small our understanding remains compared to the vastness that contains us. This framing makes wonder itself the teaching, not specific facts about orbital mechanics or chemical composition, but the experiential recognition that reality transcends our concepts. Before we measured anything, we felt awe. That awe is response to something real, the encounter with mystery, with magnitude beyond human scale, with existence that doesn't require our understanding to proceed magnificently. Cultivating wonder should be science's highest goal, not just disseminating facts. Facts without wonder are lifeless, technical details divorced from significance. Wonder without facts is empty, emotion unmoored from reality. But facts infused with wonder, understanding that deepens rather than diminishes awe, That's the synthesis worth pursuing. That's what makes 3i Atlas matter beyond its catalogue entry. It reminds us that the cosmos remains wonderful, that our knowledge illuminates but doesn't exhaust reality. If this journey reminded you of how vast and how deeply human curiosity can be, take a moment to like and share this story. It helps more seekers find their way through the dark, beneath the same stars that watched this visitor cross the galaxy to arrive here, now, as if the universe itself remembers us. The search has never truly ended. It only changes shape. From the temples of Sumer to the observatories of Chile, humanity has been chasing the same shimmer in the dark, the light of what we do not yet understand. Each generation gives it a new name: the Annunaki, divine travelers, interstellar objects. But the meaning remains the same. We are creatures drawn to questions that stretch beyond answers, to mysteries that connect us to something larger than ourselves. This continuity of purpose across millennia deserves recognition. Despite vast differences in technology, worldview, and cultural context, ancient and modern astronomers share essential motivation: to understand the lights in the sky, to map the heavens, to recognize patterns in celestial motions. The Sumerians, watching from ziggurats, and modern researchers at computer terminals are engaged in the same fundamental activity, separated by time and method, but united in purpose. The names change, but they point at the same underlying phenomena: wandering lights that don't fit established patterns, objects that appear and disappear, travelers from regions unknown. Every culture that watched the sky developed frameworks for understanding such encounters. Those frameworks reflected their cosmologies and technologies, but beneath the different interpretations lay shared observations of real events. Modern astronomy stands at the end of a long chain of watchers, each generation building on previous knowledge, refining methods, expanding understanding. But we're not fundamentally different from our predecessors. We still watch lights move across darkness. We still wonder what they are and where they come from. We still seek pattern and meaning in celestial phenomena. The instruments have improved dramatically. The understanding has deepened enormously. But the essential human response, curiosity about the cosmos, remains unchanged. 3i Atlas continues its journey outward, moving back toward the interstellar cold it came from. In a few years, it will fade beyond our instrument's reach, vanishing into darkness as completely as if it never existed. But what it leaves behind persists. Questions about origin and destination. Wonder about what other travelers drift unseen through the galaxy. The recognition that we share space with visitors from distant suns, that our isolation was always illusion. The observation window closes steadily. Each week carries 3i Atlas farther from the sun, dimmer in our telescopes, harder to study. Already it's beyond the reach of smaller instruments, observable only by the largest facilities with the most sensitive detectors. Soon even those will lose it as it fades below detection thresholds. At some point in the next few years, the last observation will be recorded, the final photons from this visitor detected. After that, it returns to invisibility, another object moving through interstellar space beyond human ability to track. But the data remains. Every observation is archived, available for analysis and reanalysis as techniques improve and understanding deepens. Future researchers will examine these measurements with tools not yet developed, extracting information current analysis misses. The physical encounter may be brief, but the scientific legacy persists. We may lose sight of Three-Eye Atlas, but we don't lose knowledge of its existence or the constraints its observations place on models of interstellar objects. And perhaps that's enough. We weren't meant to follow it forever, to track it across the galaxy until it encounters another star. We were meant to notice it passing through, to measure what we could during the brief window when it was accessible, to add its data to the growing catalogue of interstellar visitors. Each detection builds the dataset, and eventually that dataset reveals patterns invisible in any single case. The significance of Three-Eye Atlas lies not just in itself, but in what it represents. Another data point, another example, another piece of the larger puzzle. The path it traveled remains open. More will come. Already, astronomers calculate how often such crossings occur, how many pass unnoticed because they're too faint, too far, too small to catch our attention. We live at a waypoint, a place where countless journeys intersect. Most we will never witness, but some arrive precisely when we're ready to recognize them. This statement expresses both humility and hope. Humility because we're clearly missing most of what passes through our neighborhood. Our detection capabilities, while improving, remain limited compared to the total population of interstellar objects. Most visitors pass unobserved and unrecorded, their transits lost to history. But hope because the rate of detection is increasing. As our instruments improve, as our survey strategies refine, as our understanding grows, we'll find more. We'll build a comprehensive catalogue. We'll move from surprise at each detection to statistical understanding of the population. Already, predictions suggest we should detect several interstellar objects per year once survey capabilities reach anticipated levels. LSST, the Large Synoptic Survey Telescope under construction, will scan the entire visible sky repeatedly, catching everything that moves. Space-based infrared telescopes will detect objects too cold or dusty to shine brightly in visible light. Radar systems might eventually track interstellar visitors too faint for optical detection. The future of interstellar object astronomy is bright, though the objects themselves remain dim. Maybe that's what the Annunaki legends always meant. Not invasion, but intersection. The idea that when humanity reaches certain thresholds of awareness, the universe responds not with answers, but with reflections. We search the sky and find travelers. We decode ancient texts and find coordinates. We wonder if we're alone, and visitors arrive from beyond, carrying the same ice and dust we're made from, proving connection across distances we cannot cross. This interpretation treats the legends as prescient rather than accurate. The Sumerians didn't correctly describe interstellar objects, but they correctly sensed that the cosmos contained visitors that would arrive when humanity was ready to recognize them. This framing preserves meaning while abandoning literal interpretation, a synthesis that respects both ancient wisdom and modern knowledge. The reflection metaphor is apt. The universe doesn't respond to our questions in the direct sense of conscious communication, but phenomena occur that answer questions we've formulated, that address concerns we've raised, that illuminate problems we're working on. Not because the universe cares about our questions, but because reality is rich enough that sustained inquiry eventually encounters relevant phenomena. We ask if interstellar objects exist. We build telescopes capable of detecting them, and we find them. Not because our asking made them appear, but because asking focused our attention where they could be found. If you felt calm in this story, if you found yourself drifting through the same quiet wonder that binds us all beneath the stars, subscribe to History After Dark. Here, we'll keep following the trails of light that vanish beyond reason and listen for the echoes that return. Because somewhere in the vast between, another visitor passes, silent, patient, remembering. And when the next one comes, we'll be here, ready to tell its story. The invitation to subscribe acknowledges that this journey continues beyond any single narrative. 3i Atlas is one visitor among many to come. Each will bring its own story, its own anomalies, its own lessons. The work of watching, measuring, wondering doesn't end when one object fades beyond detection. It continues with the next and the next, an ongoing human project as old as consciousness itself and as new as our latest technological capabilities. The silence between stars holds more visitors than we'll ever count, but we'll count what we can. We'll measure what reaches us. We'll wonder about what it means. And in that wondering, we'll remain connected to every human who ever looked up and asked the same questions. What are those lights? Where do they come from? What do they mean? No one knows the complete answers. Perhaps no one ever will. But the asking itself matters. The search itself is the point. We are the universe becoming aware of itself, conscious matter contemplating its own existence and origins. Every measurement of an interstellar visitor is the cosmos examining itself. Fragments of ancient star systems studying fragments of other ancient star systems. We're all made of the same fundamental stuff, all products of the same cosmic processes, all participants in the same vast unfolding. 3i Atlas carries that message whether it intends to or not, that we're connected, that isolation is illusion, that the universe flows through boundaries we imagine keep things separate. The visitor proves materially what wisdom traditions have always taught spiritually, that everything is one, that separation is perspective, that deep down we share substance and origin with everything we perceive as other. Maybe that's the most important lesson, not the orbital parameters or chemical composition, but the simple fact that something from elsewhere arrived here, connecting there and here through its physical presence. The connection is real. The relationship exists. We share space and time with travelers from distant origins, and in that sharing, we're bound together in ways that transcend the vast distances. The stars aren't so far away anymore. Not when their wandering children visit our doorstep. Not when we detect and measure and marvel at what they carry. The cosmos has grown smaller in the best possible way. Not diminished, but brought nearer, made intimate, rendered accessible to wonder and investigation. Look up tonight. Somewhere in that darkness, objects are crossing through, carrying stories we're only beginning to read. Silent travelers on journeys measured in eons, passing through our moment in their epochs. We're lucky to live when we do, when technology and timing coincide to let us see them. Lucky to be watchers of wonders, descendants of a long line who gazed upward and wondered, ancestors of those who will know far more but feel the same awe. The journey continues. The search goes on. The visitors keep coming, patient as time, silent as space, carrying everything we need to know if we're wise enough to read the signs. Welcome back, travelers. We've been waiting.